So we are dealing with a very interesting problem in the NSEP 2025 segment, and this is the seventh problem which we are dealing in this series. The problem is stating two blocks A and B of masses m and 2m respectively are connected by a massless spring of natural length L0 and a spring constant K. The blocks are initially at rest on a smooth horizontal floor with a spring at its natural length L0. A third block C of mass m, identical to that of block A, moves on the floor with a speed v along the line joining A and B and collides with it elastically. In the subsequent motion, so we need to answer the following problem, and the question is based on a mixed concept of the center of mass collision, and followed by this we will also be dealing with some idea of simple harmonic motion. So if we deal with the problem is stating that the blocks are initially at rest on a smooth horizontal floor. So we can say that there is no external force involved in the problem. F external is equal to 0. The spring constant is K and natural length is L0. A and C are identical and they collide along the line joining A and B, and the collision is perfectly elastic. So the first conclusion which we can draw is that velocity of C after collision will become 0 and C will transfer all its momentum to A, that is velocity V. And it is because if two identical masses are undergoing elastic collision, then they exchange their momentum. So if they exchange their momentum, A will acquire a velocity V after collision. So now the next thing which we discuss is what happens is at maximum compression. So at maximum compression, both A and B will start moving together with same velocity. So this is also confusing sometimes for students to understand. So let us understand this. So let me draw the diagram and then we'll continue with the discussion. So over here we can say that as A starts moving with a velocity B and B was originally at rest, so A will transfer some of its momentum to B because they both are connected by a spring of constant K, and gradually they both will start moving with the same velocity or the same speed for the time or a certain time instant. So it is at this time instant that there will be no further elongation or compression of the spring, and we can say this is the condition of maximum compression. So the condition of maximum compression is when they start moving together simultaneously, where A was initially moving with a velocity v. So if we solve the problem from C frame perspective, this is a very interesting problem on C frame. So if we are solving the problem from C frame perspective, then we can say that initially the energy is stored in this form, half m1 m2 upon m1 plus m2, that is 3m, followed by v relative square, which is equal to v square, and finally it is converted into half kx square. So k and x square is the maximum elongation produced in the spring, elongation or compression produced in the spring, both being the same value which we are looking for. So if we solve for this, then we attain something like this, that we have a value which is equal to 2mv square by 3k, and then square root of this particular value will give us the value of maximum compression or maximum elongation which is possible for the spring in this system. So over here if we look at the options which we are looking for, so we do not match with any of the option over here. So the first one is saying that the maximum compression will be m by 3k, so it is not matching with the part which we have calculated. Now in the B part, the problem is saying kinetic energy of A and B together when the spring is compressed is maximum is mv square by 6. So over here we can say that at this point when the compression value is this, so if we calculate the energy stored in spring, so if we calculate the energy stored in spring, so we can calculate it as half k x square, so 2mv square by 3k, and over here we can chop out kk, 2 to cancel out, we have mv square by 3. and the total energy initial was equal to half mv square, which was acquired by block A. So over here we can say that if total energy initial is converted into potential energy of a spring and kinetic energy of A and B combined, then we can definitely say that the initial energy which we have is equal to half m v square, and it is stored as spring energy, which is equal to mv square by 3 plus kinetic energy of A plus B system, and hence over here we can say that kinetic energy of A plus B system is half mv square minus mv square by 3, and over here we obtain 1 by 6 times of mv square. So if we look at the option which is given to us, it is matching with what we have calculated, so the second option is absolutely correct. Now the problem is stating the block A and B stop for a moment when the spring is at maximum compression. Again, this statement is perfectly correct, or no, it is incorrect, because they both are moving with the same velocity. We can say that they are moving with the same velocity, so the relative velocity is 0. So I mistook this as relative velocity. So they do not stop for a moment, they stop for a moment with respect to each other, but they do not stop with respect to Earth. So we can say that the relative velocity of A and B, or velocity of A with respect to B, is 0, but A and B are moving with a certain velocity. So we cannot say that A and B stop for a moment, so this alternative is incorrect. And now we have the fourth option to check the time required to reach the maximum compression for the natural length is this much. So if we look at this particular system, so over here we can definitely say that the time period is given by t equals 2 pi root under mu by k, where mu is equal to reduced mass. Reduced mass in this scenario being equal to m1 m2 upon m1 plus m2. So we get 2m by 3 as reduced mass by k. So this is the time period of motion, and the problem is asking us to acquire the time required for maximum compression. So for maximum compression, the time required will be 1/4 of this value, as one complete cycle will consist of, from the point of collision, it will reach a point of maximum compression, then from compression to natural length, then again from natural length to elongation, then again natural length. So these are consisting of 4 cycles which we have. So therefore we can say that for the part D it will be t by 4. तो अगर अपने इसको by 4 अगर कर देते हैं, तो we get pi by 2 root under 2m by 3k, which is matching with this alternative, and hence option D is also correct. So we can say for this particular problem, alternative B and D are correct alternatives. So in this particular problem, we have covered concept of center of mass. In case if you don't know how to deal problem in C-frame, then I am attaching a link of a C-frame video along with this video. It will be very handy for you to understand how to solve problem in C-frame, so that you can understand from where we obtain this relation of reduced mass, where we are writing m1 m2 upon m1 plus m2, and also the idea of why we are not going with the traditional problem solving method, where we will first of all apply momentum conservation and then go for energy conservation. Also important for us to understand that whenever the problem is talking about maximum compression or maximum elongation, the two blocks must be relatively at rest with respect to each other. So unless until they are relatively at rest with respect to each other at that time, it cannot attain the condition for maximum elongation or maximum compression. कुछ सोच करके देखिए कि अगर A अभी B के तरफ बढ़ रहा है, तो अभी और स्प्रिंग को कंप्रेस करते जा रहा है और फिर धीरे धीरे B भी मूव करना स्टार्ट करेगा. तो फिर जब दोनों ही एक दूसरे के रेस्पेक्ट में रेस्ट पे आ जाएंगे, तभी हम लोग कहेंगे कि और कंप्रेशन संभव नहीं है. तो इसीलिए हम लोग कहते हैं कि मैक्सिमम कंप्रेशन तभी अटेन होगा व्हेन A एंड B बोथ स्टार्ट मूविंग with respect to each other at rest, that is relatively they attain velocity 0, but it do not mean that A and B stop for a moment. It is incorrect. Relative velocity is 0, but they are not stopping at that moment. So we say that alternative B and D are correct for this particular problem. So this was the 7th problem in the series of NSEP 2025.